Okay, now we're being recorded. Everything was said before. Okay, perfectly fine. So it's a great opportunity. And I'd just like to second what Jamie just said. Exactly, you're the group that we would like to talk to at the right level. Sort of a bit of background. I'm a professor of environmental physics here at ETH Zurich in Switzerland, and you might wonder, okay, this is a landlocked country. Why would you study ocean acidification of the coast of North America? Well, a bit of background. I mean, I was a professor at UCLA for many years, and I spent almost 10 years in California, first at Scripps Institution of Oceanography, and then at UCLA. At Scripps as a graduate student, and UCLA as a professor, and that's where I got essentially infected with the excitement about working in that area. In terms of scientific interests, I work primarily on sort of the question of the perturbation of the global carbon cycle. So a lot of work has focused on trying to understand the role of the ocean as a sink for anthropogenic CO2, and that essentially then led over to the work on ocean acidification, because that's kind of the flip side of the coin, of course, of this huge ecosystem services the ocean is doing in terms of removing CO2 from the atmosphere. And that's how I got into ocean acidification research 15 years ago already or more, and connecting that actually to the work we have been doing also along the West Coast, and some of that you will see later on.
So yeah, I guess that just leaves me. Sorry for joining a bit late. We were late coming back from my child's swimming lessons. Apologies for that. I'll catch up with Jamie and Nikki later on to find out more about you. But I'm really pleased that this has been able to be set up, and yeah, just echo Jamie and Nikki's words there, that this is a fantastic opportunity for us. So yeah, I'm Helen Finley from Plymouth Marine Laboratory. I'm a biological oceanographer. And I kind of sit on the fence between the biology and the chemistry a little bit. We do carbonate chemistry monitoring here in Plymouth in the UK, and I'm in charge of the carbonate monitoring system here. And we also do a lot of carbonate monitoring, particularly at the Atlantic Ocean and up into the Arctic. But I'm also sit on the Executive Council for the Global Ocean Acidification Observing Network, and I am co-chair for the Northeast Atlantic Observing Network for GOAN, the regional hub. So I kind of have a few different hats that I wear. One is the kind of communication of GOAN and ocean acidification and trying to bring people together. And working with people like Jessie and the OA Alliance has been a great kind of coming together, I guess, over the last year, really, where we've kind of been working together quite a lot in a few aspects. Yeah, so I'm really here in terms of understanding ocean acidification, what that means for the biology, the impacts, and bringing that network together, really. On the proposal that we are putting in, I will be leading the work package on impact. So I'll be the main contact person between kind of Jessie and you guys in the resource community and the end users. So I'll be the main contact point for any communication that goes forward for that. So it's a fantastic to meet you all. And I'll hand back to Jamie, I think, for the presentation of the Ocean Soda work.
Thanks, Helen. And you're in good company taking children to swimming classes as far as this team goes, I think, for sure. And really quick, before I turn it over to you, Jamie, any questions or comments from PCC team before we get started with Jamie's presentation? Okay, so I think we'll do 15 minutes or so, Jamie, followed by, we have the hour, so we'll do 15 minutes or so. No stress on timing, of course, it's a little longer, and then we'll just sort of use the rest of the hour to have questions from this team to you, and then end with 5 minutes or so of next steps. And for context, Nikki, Jamie, Helen, this group meets every other week, Friday at this time, so you know where to find them, and we've got sort of a built-in structure for convening as we need to going forward, follow up from this call. So Jamie, over to you.
So hopefully everyone can see my screen now. You should see a large blue scene from space.
Looks good.
Okay, so thank you very much for this opportunity. And hopefully what I'm about to talk about and show and what Nikki will then present after me is of interest to you all. So this is a view from the International Space Station, and it really encompasses the reason why I want to try and why we are developing methods for studying the ocean carbonate system from space. So everything you can see in this view is ocean. So this is a large part of the Pacific Ocean. And clearly there's a lot of interactions and areas where you can't see stuff. There's clouds, and so it doesn't mean we can see everything all of the time, but clearly this is the only way that you can have a large spatial scale synoptic view of the oceans, and therefore exploiting space assets, including satellites, is key to that. So this work, as I mentioned before, we started this back in sort of 2013, 2014, and the key for this was that we identified that because of the new ability to observe salinity from space, this key component really unlocked the ability to observe the ocean carbonate system. And we first identified this opportunity back in 2013, 2014, where we identified what you could potentially do and which areas we could potentially study. We then convened an international working group to look at this in more detail in terms of where and specifically how different satellite observation opportunities could be used to study all aspects of the marine carbonate system at the surface, but also with vertical flow and some information about the flow through the water column. This work led to some press coverage, and for example, this one here, ocean acidification now watchable in real time. The kind of the essence of what they're trying to say is the fact you can now observe, based on the work I'm about to show, you can observe the marine ocean carbonate system from space. But watchable in real time is really kind of stretching it a little too far. But hopefully what you can see kind of the essence is really there, and they were kind of right. The Huffington Post was kind of right with its headline. Now, a lot of this early work we did focused on empirical approaches. So the key was the observations of salinity from space, which is what you can see at the bottom here. This is the Amazon. So you can see the sort of part of South America, and then the blue areas you can see in all of the plots. So the Amazon plume, the water coming from the Amazon and then splitting out and flowing into the ocean. And because we were able to observe salinity, there's a strong correlation between alkalinity and salinity, and then this and the same for inorganic carbon, total inorganic carbon in combination with temperature. But this meant that you can essentially have satellite observation-based observations of alkalinity and total dissolved inorganic carbon. This is work that we have since published, and we extensively evaluated the accuracy of these approaches. We did like an optimal combination where we looked at all possible inputs, all possible published algorithms, and then we ranked them all so we can identify for which region and in which portion of time, which combinations of inputs and algorithms are actually performing the best, and where the performance is evaluated based on in situ data. And then within this, we then enabled us to demonstrate how you can then resolve the whole carbonate system. Because the carbonate system is controlled by thermodynamics, we had salinity. We previously, and we, since the late 1990s or early 1990s, we've been able to observe temperature from space. So this combined with information of the fact we're studying the surface water, so we can have some understanding of the water pressure. It means you can then resolve the whole carbonate system. So you can then, for example, look at the partial pressure of carbon dioxide, as well as the pH of the water. So that was our initial work. Then in the current project, which is about to finish, we then started to study much wider a field. So we looked at global data and observations, as well as focusing on the areas you can see in the boxes. So this meant we could study the freshwater discharge from major rivers, including the Amazon, Congo, Mississippi, and St. Lawrence. We also had a focus on looking at eastern boundary upwelling systems. So, for example, the Californian current system, as well as Benguela. We had some work, which I'll touch upon in a second, looking in the Arctic regions. And collectively, this means that we had both this kind of regional focus, but also a global capability. As part of this, part of the early work, we realized that one of the limiting factors to the overall accuracy and the uncertainties in our ability to observe a carbonate system from space was really the algorithms that we're implementing. So within the first part of the current work, we actually went back and looked at the algorithms in depth and identified what were the causes of the inaccuracies or the higher uncertainties. And this allowed us to retrain the data sets by collating, we essentially had to collate a massive consistent database to allow us to retrain the algorithms and then reevaluate them. But this work meant that previously the accuracy of the algorithms was around 10 micromoles per kilogram, and we were actually enabled to bring that down to about 6. This means that the combined accuracy of these satellite observation approaches in these regional cases can be as good as about 15 micromoles per kilogram. So to put that into context, a good laboratory, a bottle analysis of water would have a combined uncertainty of around sort of 8 to 10 micromoles per kilogram, which, given the fact that the satellite is orbiting 600 kilometers up, is a pretty unbelievable performance. We've also looked at this in terms of coastal algorithms as well. The coastal accuracy is the uncertainty is poorer, so it's at around 27 micromoles per kilogram for the algorithms themselves. But the approach we've taken means that we are now able to actually pick and focus on particular regions and then refine the algorithms as we have new data coming in, both from satellite observations, but also from in situ and locally collected data. So as a result of this kind of algorithm development, we then had 4 clear studies, scientific analysis and impact studies linked to the different pieces of work. So I'm now just going to very briefly go through these. So we had work studying first on extreme acidification and compound events. So these are where we have occurrences of, say, marine heat waves with extreme pH values. We looked at large river outflows in terms of carbon flow from the land to the ocean, but also in terms of the impact they're having on reef systems. We had looked at Arctic fish stocks, and also we had a section which is studying upwelling systems. So first of all, to look at the extreme oceanification. Because the work in the algorithm work within the current work actually also enabled us to produce global estimates of global observation-based data sets of the carbonate system. So using similar methods to what I talked about, in this case, it's exploiting machine learning approaches. We're now able to have a long time series of all the different carbonate system parameters on a global scale. So this is at 1 degree by 1 degree resolution, which is about 100 kilometers by 100 kilometers for each grid box. But this means you can then start to track, for example, pH through time, and then from that identify when extreme events are actually occurring in a particular region in space and time. And these are data and approaches that have now been published. For river flows, this focus, for example, on the Amazon plume here, and you can see this region of green and orange. These are reef systems, which are marine protected areas or monitored reef systems. And here we were looking at identifying the low pH water flow from the river and how it is interacting with these different marine protected areas and monitored reef systems. And because we're able to identify which are the best algorithms for actually doing this from using space observations, we can then identify which reefs are likely being impacted by very high variability in their marine carbonate system versus those which are having a much more stable set of environments. With the pretense or the reason for this work is there is an understanding that reef systems which are experiencing now very high variability in the carbonate system are more likely to be able to handle slow, sort of long-term slow changes in the carbonate system. And so from this, you can identify which reefs are likely to be more or less vulnerable to long-term changes. We have also looked at upwelling systems. And with this, we actually developed a satellite observation-based method for characterizing both the vertical flow of the water as it's drawn up from by the upwelling winds, but also as how the water then flows offshore. And we showed that these observation-based flows were actually consistent with the independently determined long-term trend in the pH within the water. So essentially, these observations were consistent with the changes we were seeing in the carbonate system. And you can see the example here for the Californian coast in Baja, California. So this is work that's also been published. And finally, we had a PhD student who was looking at Arctic fish stocks. And here she essentially identified the needs and the fact that the majority of economically important fish stocks in the Arctic, we don't really understand how ocean acidification is impacting them, particularly in all of their key life stages. And from this, she was actually able to identify a roadmap for how satellite observations are in fact key for understanding and managing those Arctic fish stocks. So all of the results from this existing work are all now published. We have some more work which is actually being written up to be published as well. All of the software is open access and freely available. All the data are also freely available. We have long time series, global and regional data sets. And all of this work has been done at 1 degree by 1 degree resolution and monthly time steps. And we have also tested the ability to and evaluated the logistics of providing data in a sort of quasi near real time provision. So for example, every 3 months, we can very easily update the observations for the whole carbonate system for the preceding 3 months. So in some ways, we're now at the point where we're much closer to what the Huffington Post stated in the fact that we can observe these the marine carbonate system from space, but we're sort of in real time, as they would imply, but we're not really. It's not, it's still in a delayed mode. So I just wanted to end on what we're now working on, and I just stop sharing my screen. What we're actually now working on is that we have put in a proposal to the European Space Agency, or we will be submitting it on Monday, in fact, which will take what we've developed so far and build upon it. So here we're actually intending to increase the spatial resolution of the data. So rather than having 1 degree by 1 degree, we're heading towards a quarter of a degree. So that's the equivalent of 25 kilometers by 25 kilometers grid boxes. We're also looking at taking it instead of a monthly resolution, actually heading down towards 8-day observations. And we're particularly focusing on 2 regions, one of which we'd like to focus on is the Californian upwelling current system, which you're all very focused on. And also we intend to look at the Western tropical Pacific, and particularly regions around island nations. And there are science studies within that proposal in terms of understanding more about compound events, particularly hotspots, areas of interest, areas where animals and ecosystems are particularly under stress or likely to be experiencing stressful conditions. But also there's this key component, as Helen alluded to, where we have to have this interaction between people who want to exploit the data sets as well as the scientists who are developing them. And so we have proposed to have this iterative process where we actually provide available example data. We discuss what's useful, what's not useful. Potentially as the impact case users can actually tell us what you need to help inform governors, inform policy, inform users within your regions. And the idea would be to then make all of the data available in some sort of, not in real time, but in a sense that we could provide you with long time series from 2000 or decadal 10-year time series, 2009 to present day. So you can actually start using these data. And we have 2 different ways we can do that, one of which is an online portal, an equivalent to what you can see at the moment. This is actually the same system, but they're using it here for looking at salinity and ocean currents, so the ocean currents are all the wiggly lines you can see. But we have an offline version of the same portal, which enables you to actually analyze the data and plot them and pull them out and manipulate them to a much more greater degree than what you can do with the online portal. So that's really the bit we're really interested in interacting with you all on, is actually using these observations, telling us what works, telling us what's useful, what's not useful, and how we can make them more useful to actually support your decision making. So that's really where I wanted to stop. I think Nikki is also going to talk some more about what we've been doing recently towards the end of this project.
Okay, are there any questions immediately? Or should I go ahead and start talking about my contribution?
Why don't you go ahead, Nikki, and then after that, we'll just have open questions.
Okay, good, perfect. All right, I'd like to talk a bit about the specific application of this data set, but also include some modeling study that we also will use more intensively now for the planned project. And one application is the role of extremes, and in particular, extremes that may not simply occur with regard to one potential stressor, but actually with multiple stressors, so that we events that we call compound events. And I kind of call them double whammies when two of these stressors occur at the same time, such as, for example, the one you've talked already in your introduction, for example, when ocean acidification and low oxygen concentration coalesce. But we also have actually situations where, for example, these things can occur all at the same time, what I call a triple whammy, when ecosystems are super stressed because all of these stresses occur at the same time. And I think now we have actually observations slowly in place, but also definitely from the modeling perspective, where we can start to address essentially such multi-stressor events. And I would like just to highlight what we're up to and also give you a little bit of an impression of what more can be done as we move ahead. So the first thing I'd like to talk about is these dual events, double whammies, when a heat wave and actually a very low pH event co-occurs. And this is a global analysis here of, on the left-hand side, the intensity of marine heat waves. And you can see that the Pacific Northwest is one of the, Northeast is one of those places that where we have particularly hot, strong heat waves. I think the blob I will mention later is a perfect example of that. But the interesting aspect is that actually this data reconstruction that we have put together on a monthly time scale, also at 1 degree, allows us now also to assess pH extremes. And if I look at the intensity of those, then I actually see that the Pacific Northeast is actually also a region of rather intense pH extremes. So this is now done an independent analysis. So the question is, well, do they actually co-occur? And the fact is that is actually starting to happen. So this is a time series in blue of over the last 30 years, a bit more than 30 years of marine heat waves in blue. Then the occurrence of pH extremes. We have a very rapid increase of those pH extremes as we're acidifying the ocean. It's a very strong trend. And as a consequence of that, we start to see essentially these compound events when conditions are overly hot and overly sour at the same time. This situation, let's say if you just go back 10 years ago, tended to be such that these events tended to be separate. So for example, here is a situation in March 2011 where we had essentially a tropical pH event, and we had for example, Tasman heat wave, but these events did not happen. They tend to be independent of each other. And now if you scroll forward and go actually to July 2015, and again, if you focus on the Pacific Northeast, we see that actually now suddenly we have co-occurrence of marine heat waves and these low pH events that we call ocean acidification extremes. And this happened exactly during the blob area. And so that what I'd like to do next is to show that we can actually now combine this satellite-based view that I just presented you also with modeling studies to go actually even beyond heat and temp and CO2, including also oxygen, that at the moment we do not have access to from the satellite perspective. So for that, we're using actually a modeling system that we have developed over the last few years for the US West Coast. It covers actually the whole Pacific, and we run this so-called in hindcast mode. So we force the model with observed fluxes of heat and fresh water, as well as observed winds. And we analyze essentially the extremes in that in the same way as before. But we actually can now go beyond the surface, and that's one of the restrictions we have with satellite observation. We can actually look at depth. And what I'm showing you next as a movie is actually extremes in the different parameters, and the intensity of the color gives you a sense of how deep actually these events are. So if it's full colored, then actually that means it's a very substantial fraction of the water column, and we're looking here at the top 250 meters is affected. If it's a light color, only a small fraction is affected. And now you can start to watch this animation, and anywhere you see essentially these extremes. So now we have heat extremes, temperature extremes in red. The blue is now oxygen extremes. As you can see, what we have is essentially very rich mesoscale eddy-driven anomalies also here in pH. And now we start to zoom in on the US West Coast. And I can start to see actually here also very coastal events that are all actually associated with coastally trapped waves, but also upwelling events that you see every once in a while are popping up here that are actually oxygen extremes at the same time as temperature extremes. And now as we move further and further into the blob period, you start to see that, and we essentially start to see triple events where we have essentially all events or all properties being extreme at the same time. And the red areas essentially is the area of the blob events indicated with this. So you see a very complex evolution of these extremes in time and space. Some of them are very coastally trapped, associated with upwelling events, with filaments, for example, very powerful mechanisms to generate extremes, offshore propagation, but also large-scale forcing of these extremes. So the whole zoo of things are happening here, all of which essentially have then impacts on marine organisms. And what that impact is actually sort of one of the big questions that we have. Just to illustrate how serious actually the blob was in terms of not only being a heat wave, but also being a low oxygen event and actually a low pH event, shows essentially this color graph on the left-hand side, which is for July 2015. And where it's black, we have essentially the whole area here is actually triple whammy. So, but you see also along the coast of California and Oregon that we have actually blobs of triple whammies. We have the heat waves, we have a bit outside, we have actually low oxygen concentration coalescing with the heat waves, et cetera, et cetera. So this was a pretty bad period in the region. And on the right-hand side now we see kind of the depth extent of these extremes indicated over the rectangles here on the left-hand side. So here are average profiles in terms of anomalies. So it was anomalously warm down to almost 200 meters. The oxygen level was actually anomalously low, but it was a bit anomalously high below that. And then pH was pretty much low, anomalously low throughout the water column. So one of the big questions we have is actually, well, in the massive ecosystem impacts that we have seen during the blob, whether or not some of those were actually not just responses to the massive heat wave, but also the fact that these conditions during this period, the pH was enormously low as well as oxygen. Just to sort of put this in context here, this is the time series of this particular region. And I'd just like to focus here on the very end of the time series where we start to see this triple whammies occurring. And so this is just an illustration of where we are right now. And I think the message here is that extreme events, I mean, those sort of episodic events where things are much more extreme, much more stressful for the organisms and the ecosystems, that these extreme events are developing very rapidly and extending now over larger and larger regions. A lot of that trend is human driven. And the blob could have been one of those signature events. We're not 100% sure yet, but everything that we have analyzed so far would indicate that it has been. But one of the big questions moving forward is, okay, can we now connect essentially these reconstructed events with ecosystem impacts? And a lot of what you're doing actually in terms of monitoring and coalescing now your chemical observation with biological observation could be enormously helpful to make actually that connection. So thanks a lot. And now I think it's time for question and further discussions.
Thanks, guys. That was awesome. And I know that there will be a lot of questions. And I think, and obviously you've got an audience that's familiar with and engaged in blob management, for lack of a better word, and thinking about future predictions and forecasting. So maybe given the time, I'm wondering if we might just go around by each state and ask for your, if there are specific questions. You know, I think the proposal in front of this team is that we will now engage together as, you know, funding for the project is approved, I guess, or is generated, and that we would be one of a couple case studies to work with Jamie, Nikki, and Helen on a series of Zoom meetings just like this to have a little bit more questions and call and response of more or less, what are the best uses of this tool for you? And that would be, you know, curated over a series of 4 or 5 engagements, or potentially more if we feel really animated. And so that's sort of what's in front of us as an opportunity. So I don't want to go down a rabbit hole of questions that can be explored in those further dialogues. But I'd love maybe to get top line takeaways from each state, general reactions to, yes, I can see there's a lot of applicability to this tool in our state and as a region, and maybe have a little bit of just your first line reactions, and we can go into questions in more detail at later sessions. So with that, Liz, I'll turn it over to you. I see your mic off.
Hey, first of all, really great presentations. I really enjoyed it. I'm pretty excited about this. My initial reactions are that I think this is a useful product to us as we continue to try to integrate that biological and oceanographic data, you know, including the source from the satellites. Future discussions, I have a lot of questions about your satellite data and specifically how close to shore, the shoreline, you can get your resolution to, since that would really kind of establish the utility for some of our applications. And then I'll just jump over to Dave to see if he has any additional thoughts.
Yeah, thanks, Liz. Yeah, lots of great information, lots to process. I guess, yeah, with Liz, I see this generally being useful. I like the, you know, what you said about trying to increase the spatial resolution, because, you know, if you think about when we're down, you know, kind of at state level, you know, managing things, you know, our shelf off of Oregon is pretty narrow, you know. So if you have a 1 degree grid, you're including, you know, the shallow near shore, you're including the shelf, you're including the continental slope. In most cases, so you're including you know, it's integrating a big area that has a lot of internal variation. And so I think going down to a 1/4 degree will help a lot. but even that, are just thinking about hypoxia, often it's a pretty localized phenomenon, in at least on the Oregon shelf. There's some of those extreme years when like the whole shelf practically goes hypoxic, but in most years it's spotty and kind of unpredictable. So if there's ways to think about scaling it down further, maybe not so much as a full imagery type product, but if there's some other methods to help scale it down, that would be great. But even without doing that, it's definitely useful. Then I have a lot of questions about connecting it to which we could maybe talk about like in future meetings, but connecting it to actual organism impacts. It's sometimes hard to connect a large scale kind of picture to more site specific impacts for organisms. You often could see the indirect connection. You could see the blob event, and then a couple years later we see these big declines in kelp forests in Northern California and Southern Oregon. So you can kind of see these big picture events, but it's difficult to make that direct connection when you have kind of a large scale picture. So I'd be really interested in learning more about connecting this to direct effects on organisms. I think that obviously that's an important part from a resource manager's perspective.
Great.
Yeah. Other than that, it's excited about this and want to learn more.
Thanks, Dave. That's great feedback as well. And begging folks, if you have 3 or 4 minutes to stay after the top of the hour. But Washington, Jen, Micah, first top line reactions.
Sure. Super excited to see this work. Thank you for sharing it. I think, from my policy standpoint, I sit in a slightly different place, and I see the utility of this kind of work to help in communication. And in particular, sort of documenting, we've been highlighting the blob and the impacts of the blob, and our concerns about the future, where are those trends headed? And so I do think that hindcast of like the historical time series helps paint that picture of a changing ocean, and helps highlight the need for action at the policy level. So I think that's the part that I get excited about, is being able to translate the science in a way that's useful in communicating both to the public, but also to policymakers. And then, as Dave mentioned, we have regional fisheries management that's occurring off our coast. And so I do think that that's a place where being able to adapt how we manage our fisheries, which are really important to our coastal communities, this kind of data will be really important for that. And I like the idea of being able to have a project of this scale to help us as a region together, right? Because we have our individual efforts, as you've heard, in terms of monitoring, but being able to paint that bigger picture is really useful. So look forward to it. I think it's a great opportunity. Thanks so much.
Mike, anything you want to add there?
Sure, I'll just add, I think that captured a lot of my thoughts. For one specific thing, I do feel like I'm helping this new effort to develop a sentinel site off of Washington's coast as part of a marine sanctuary there. And over the next year, we are hoping to settle on an easily digestible indicator that is visualized off the coast. And as I was thinking about all the challenges and geographic downscaling, this is actually one application where we would not need really high resolution estimates for nearshore areas. The more important metrics are broader off-shelf estimates of water quality that would determine success of Dungeness crab or other fisheries. So I know that there'd be lots of work in plugging into the products that you're generating, but that one to provide data for this Sentinel site, I think has a lot of potential that I see immediately, because there's really limited potential there to take more measurements. It's not practical really. So satellites would be an amazing way to fill that gap.
Great, thanks, Micah, taking notes on that concept. And last but not least, no small thing, the California coastline. Anything? Go ahead, Justine.
Yeah, I think I echo everything that's been said already by our sister states. I'm also interested to learn more about the spatial resolution in particular, and how the natural variability could be captured or messaged within the grid size, the quarter of degree or whatever it might be that you would be looking at, echoing Dave Fox and the amount of variability that we do have, particularly in the upwelling zone and when you get closer to shore. So I'm very interested to see, to understand more about that. What we're losing though in spatial resolution, I'm excited about gaining in temporal resolution. So I think that's a really exciting part of this work, and the ability to create time series. For California, we have a goal, a project to develop similar to building on Micah, but this is statewide, a report card of ocean and coastal health, so to speak. And so we've been discussing options for ocean acidification indicators, and I think, and other ocean chemistry stressors. So I think in terms of developing a time series and communication, as Jen was saying, there's real potential I see here to develop a sustained communications time series around some of these stressors that we could integrate into all of our products that could tell a story about changing chemistry. And so I think that would be really useful for California. I'm a little bit skeptical about the biological connection just because of the spatial resolution. So again, I'd really be interested in more conversations there. Anything to add, Kat?
No, I think everyone covered it.
Yeah, thanks for the presentation.
Yeah, it was great.
Well, thank you all. This was a good morning. I was looking forward to it. And I think for next steps, maybe Jamie and Nikki, you can tell us what you think next steps are as far as timeline. And then obviously I'm hearing resounding interest, and we can talk as a group together about what that commitment means and looks like, and time expectations, etc. But I'm hearing a general green light to hear what next steps are from you guys.
Yeah, that all sounds brilliant. It's brilliant and really exciting to see so many people that are really infused and can see uses for this work. So that's quite blown over by that. In terms of the timeline, we submit the proposal on Monday. We have typically they take about 3 months to review. So we should hear something in sort of September, October time, and assuming we're successful, we would expect the project to start either in 1st of December or 1st of January 2022.
Okay. And the project being over the course of 18 months or so, is that about right?
Sorry, I didn't catch that last.
Sorry,
last
the project for sort of the project, particularly around the stakeholder engagement and thinking about the comms products or products in general, is about an 18-month horizon beginning whenever the project starts or so?
Yeah, so the project would run for 2 years. And yes, we would want to start engaging with you from about month 2 all the way through to the end, really.
Well, that's great. I think given time, what I would suggest is, like I said, this team, we are a tight group. We have worked together for several years and meet every other week and have various projects, including some of the managed steering of the Alliance as well, the OA Alliance. So what we'll do is we'll probably meet again 2 weeks from now and digest a little bit of this together. One thing I might suggest is we could put together a series of written questions if we have any follow-up for you directly, even around the logistics of what it would mean to engage as a stakeholder partner. But I think we're keen and interested. And then I think, I don't want to ask too much of your time or the 3 of you, but I think getting together once or twice more, even for an hour before December. You know, would be a good opportunity, as you guys have time, just to do a little bit more call and response, so we can really hit the ground running 2 months into the project, as long as we get the green light. But that's sort of my general proposal, if that sounds all right. And Helen, I know how to find you.
You do, and that does sound great. I mean, even if it's just a couple of us, each one, or whoever, then I think having that communication would be great. And even if heaven forbid we don't get the green light for this proposal, I think this sort of communication is fantastic, and hopefully we can move this sort of work forward through the Go On network and other projects as they come up anyway. So this sort of discussion is brilliant. So it's not wasted, even if worst case scenario this particular proposal doesn't come to fruition. But hopefully, fingers crossed, we have a good standing to get it funded. So hopefully more will come.
Yeah, and maybe just to finish here from my side, I think the fact that you're so excited about sort of receiving that information is also a very strong stimulus for us. I mean, to push forward, and probably some of the developments we already start, even if we don't have the final go on the project, because I mean, it's also interesting for us, but having that extra layer is extraordinarily welcoming for us.
Jamie, go ahead.
Yeah, I've taken lots of notes during this meeting, so there's lots of things I can now add, bits of information, key uses and that kind of thing to the proposal. It's really good. But just to reiterate, Helen's point is just to manage expectations. It is an open call, the funding that we're applying for. We have done a lot of this work with the European Space Agency previously, so this would be the third project we bid for, and actually the fifth carbon-focused one that I bid for. But it is open call, so it's not. It will be assessed on a bunch of criteria, and it's not a guaranteed process. Someone else may bid for the same money, we don't know. So.
Okay. Well, that sounds good. It sounds like we'll stay connected. We'll keep our fingers crossed, and we'll remain friends as we go forward. So, okay. Well, that sounds great. Thank you all so much for your time today. Really great presentation, both, and happy weekend, everybody. And hope, I guess, as we move forward in this in this decade. Hope and attitudes.
Okay, thanks a lot for your time. It was very interesting indeed. Thank you.
Thank you.
Yeah. Thanks very much.
Thanks, everyone.
Thank you.